So this is from the year 2011. It is a type 4 problem mainly because of the fact that we're doing a rotation. I also classify it as a type 7 problem because there's this extra piece of information about related rates and this extra piece of information about arc length. So first and foremost, while it doesn't ask you to find the area of region R, typically type 4 problems have that question. And the area under a curve is calculated as the range 0 to k, or the interval 0 to k of e to the 2k dx. Now, let's do this as 2x. Okay. That gets you the area. Now, it didn't ask us to do the area, so that's not part of the problem. But this accumulates the area from 0 to some x value k. Part A, it does ask us to do something. In Part A, there's two approaches. In class, we've learned the parametric approach, which ties very close to the function, or I should say the rectangular approach. So there's two different approaches. Our goal is to find the perimeter around the region. And very quickly you can say, well, the length of this side is 1, the length of the base is k units, the length of the right-hand side is, well, the height of that, the y value, e to the 2k, and then the last piece is, what is the length of the curve? And in parametric, we learned that the length of curve can be calculated by doing dx dt squared plus dy dt squared and put that under a radical. However, our curve is not in parametric form. It's actually expressed as a function. If you were to parameterize it, you could use this. But the relationship between this equation and the function notation is when you parameterize it, you replace x with t. So if your x coordinate is t, what is the derivative of t? 1. And so the derivative of x is 1, and the derivative of y would be f prime of x. So whether you're in rectangular coordinate systems or in parametric, the relationship should be fairly synonymous between the two. So part A, we get the answer 1 plus k plus e to the 2k. Oops, I forgot to write that up there. E to the 2k plus, oops, and we integrate those. The integral of 1 plus f prime of x would be 2e to the 2x squared dx. And we're going from a x coordinate of 0 to an x coordinate of k. The point breakdown is if you have the f prime in there, that's worth 1 point. If you are able to get the integral, that's 1 point. And then finally, if you have your answer, which is basically the whole thing, that's worth 1 point. So it's kind of a tiered approach. Moving on to part B, the region R is rotated about the x-axis to form a solid. So this is one of those problems where you ask the question, what is going to be better, shells or washers? And you may be more comfortable with one. It is my opinion that in this case, rotating washers makes more sense. And our general go-to formula for rotating washers is big R squared minus little r squared dx times pi. So you've got your outer radius and your inner radius. So we need to establish then what is the big radius and what is the small radius. The big radius is defined as top minus bottom from there to there. And the small radius is defined as top minus bottom from here to here, because there's only one function. So actually our small radius doesn't even exist. There's no hole going through the washer. But if we're being consistent to all possible cases, big R would be the top function, e to the 2x minus the rotation line, which is at 0. And the little r would be the top function, which is 0, minus the rotation line, which is 0. So those disappear, all those zeros cancel out, and we get the equation pi big R squared dx, and those washers stack up from 0 all the way until k. So the point breakdown for this is, first you get 1 point for having the integrand correct. Then you get 1 point for having the limits correct. You get 1 point for finding the antiderivative, and the antiderivative of e to the 2x squared would be 1/4 e to the 4x. That's the antiderivative, and it gets evaluated from x equals 0 to x equals k. So your last of the points is the final, oops, and we need to include that pi there, I forgot the pi. Okay. So your last point comes from having that. The volume found in part B changes as k changes, and they tell you dk dt equals 1/3. So we just established that that volume we found was pi fourths e to the 4k minus pi fourths. And they're telling us that the volume is changing as k grows. Find the rate of change of volume. This is a related rates problem, find when given. So they're asking you to find dv dt when k equals 1/2, given the rate dk dt is 1/3. So we take our volume equation and differentiate with respect to time. dv dt equals 4 pi fourths e to the 4k times dk dt. So there's our implicit differentiation. Then they want us to find out what the value is when k is 1/2. So we can plug 1/2 in for k. 4 times 1/2, and the dk dt is 1/3. This is the complete unsimplified answer. If you'll notice, the 4's cancel, the 4 times 1/2 cancels, and we wind up, if we simplify our answer, getting pi e squared over 3. The point breakdown for this one is you get 1 point if you did the chain rule, and then you get 1 point if you arrived at the right answer.